Hello everyone. Today we are going to learn on the chapter Logic Gates. Let's try understanding what you mean by gates. Now gates is nothing but digital circuits where your input or output signals could be either low or it could be high. Now these logical gates are specially used to create certain kinds of circuits for motherboards. Let's see what could be the definition of logic gate. A gate is an electronic circuit which operates on one or more input signals to produce a single output. That becomes the definition of logic gate. Now, logic gates are classified into two types. One is basic gates, the other one is derived gates. So again, basic gates are further divided into three types. They are NOT gate, which is also called as an inverter gate, an OR gate, and an AND gate. The derived gates are further divided into four different types, that is NOR gate, you have NAND gate, you have XOR gate, which is also called as an exclusive OR gate, and XNOR gate, which is also called as exclusively NOR gate. Now let's understand what do you mean by basic gates. Now as I said, basic gates are of three types. There is NOT, OR and AND gate. Let's see in detail as what is this basic gates. First, try understanding what do we mean by a NOT gate. A NOT gate is also called as an inverter gate, where the input is A and output is the complement of A. So whenever we try giving an input for this circuit, it is always the opposite of what we give as an input. For example, if you look at this truth table, the value of A, that is input, if it is 0, my output which I get it is 1. If my input is 1, then I would get my output as 0. So NOT gate is nothing but whatever input we are providing for the circuit, we get an opposite of that, which is also called as complement of an input. Now let's see what do you mean by an OR gate. OR gate has two or more input signals but produce one output signal. But what do you mean by OR gate? OR gate is nothing but when we add two input signals to produce one output. But the truth table says that if any of the input signal is high, that is 1, then output will be high. In other cases, it would be low. If you look at the diagram, this is the symbol for NOT gate. This is the symbol for OR gate. We have two inputs A and B. We have an output as A plus B. The symbol used for OR gate is A plus B. When I have two inputs for truth table, I have separate columns for A and B. The values of A is 0011, B is 0101. What I get an output is if I add the values of two inputs A and B. So 0 plus 0 is nothing but 0, 0 plus 1 is 1, 1 plus 0 is 1, 1 plus 1 is 1. Similarly, I also draw a truth table for three inputs. Now whatever I'm saying here, this is an input for two variables. If I have input for three variables, the truth table goes like this, where we have 4 zeros, 4 ones, 0011, 0011, 01, 01, 01, and finally we get the output after addition of this. So what is the rule of a OR gate? OR gate is when any of the input is high, that means if any of the input is 1, then I get result as 1. In other cases, I get the value as 0. The same thing applies for three variable as well. Now if I want to draw the symbol for more than two inputs, it is like this. It goes like this, A, B, C. If it is for four variables, we write it as A, B, C and D. And this was about OR gate. Now let's understand what is an AND gate. AND gate is nothing but a multiplication of two inputs. It is again where we have two inputs and one output signal. Now the rule of AND gate says that when all the inputs are high, that means when all the inputs are 1, then output is also 1. In other cases it is low, that is 0. If you look at the truth table, 0 multiplied by 0, I get output as 0. 0 multiplied by anything is 0. So 1 multiplied by 1, it's 1. So this is a truth table for two inputs AND gate. So if you look at the symbol of AND gate would be represented in this way with two inputs. Represent a symbol for three inputs. It is, the symbol is like this. If we go for four variables, the symbol would be like this. The same logic, if we apply truth table for three variables, it goes like this, where we again multiply all the values, we get 0. The output would be high when all the inputs are high. This was about basic gates. Now let's understand what we mean by derived gates. Derived gates are nothing but the gates which are derived from basic gates. Now let's understand what is a NOR gate. A NOR gate, it is nothing but a NOT gate followed in front of an OR gate. That becomes your NOR gate. A NOR gate has again two or more input signals to produce one output signal. So the rule goes for NOR gate as if all the inputs are low, that is 0, then the output is high, because it is complement of an OR gate. That's why we represent it as N. N means NOT gate, NOR gate. So we have two inputs here. It's similar to your OR symbol, but the only difference here is we get a bubble in front of this symbol, and this represented as NOR gate. And if you look at this, in OR gate we write it as A plus B, but when we go for NOR gate we put a complement of over the variables, and that becomes NOR gate. So if you look at the truth table, it is 0 plus 0 because it's an OR gate. So 0 plus 0 is 0, but this is not an OR gate, this is a NOR gate, and that's why your 0 becomes 1. It's complement of that. And similarly all the values follows the same logic. Now this logic applied for the truth table for three variables, and these are the symbols for more than two variables, like 3 or 4 variables. So the other way of writing the NOR gate is like this way. We can draw the OR gate, and in front of that we can add a NOT symbol. Now let's understand what is a NAND gate. NAND gate is nothing but a NOT gate which is followed by an AND gate. So if you look at the symbol of an AND gate, it's similar to your AND gate. The only difference is we find a bubble in front of a NAND gate, and this symbol is called as a NAND gate. So what is the rule for a truth table for NAND gate? If all the inputs are high, then the output produced is 0. Now if you look at the inputs, 0 multiplied by 0 because it's an AND gate, so 0 multiplied by 0, but the output we are getting is 1. It's because it's complement of an AND gate. So when we get 0, the opposite of 0 is 1. The same logic is applied for other values. So this truth table is again for three variables. That was about NAND gate. Now let's go for XOR gate, which is also called as exclusively OR gate. The exclusive OR gate is similar to your OR gate, but the only difference is we get one more symbol over here, and that represents your XOR gate. Now here also we have two or more inputs which produce a single output. But what is the rule of XOR gate? It is your output is 0. In the truth table the output would be 0 if there are even number of ones in an input. That means if I check there are even number of ones in an input, then that case I get output as 0. So if I check I have two ones here, so I'll get output 0. If I have odd ones, I get output as 1. So if I have odd one, I get 1. I have two ones, that means even, I get 0. So the same thing is applied for XOR gate for output 1 when there are odd number of ones. And this is again the same logic applied for 3 variables, and this is a symbol for more than 3, 2 and 4 variables. Now let's try understanding what is XNOR gate. XNOR gate is also called as exclusively NOR gate, and this is followed by NOT gate for XOR gate. Now XNOR gate is equivalent to inverted XOR gate in a truth table as well as a symbol. The XNOR symbol is represented with the help of XOR gate, and in front of that we put a bubble that becomes XNOR gate. The rule for this truth table is the input combination has even number of ones when the output is 1. Let's see what will be the input and what will be the output. If my input is 0 0, then my output is 1, because it is nothing but what 0 plus 0 is 0, and complement of 0, it becomes 1. Similarly for 0 plus 1, it's 1, the complement of 1 becomes 0. Same logic is applied for other truth table values. That becomes your XNOR gate. Now let's try drawing certain circuit diagrams for a given expression. Let's say we have given an expression with 3 inputs, that is A, B and C variables, which is equals to AB plus AC bar plus B bar, A bar, C. Now how to represent these circuits? So far we have understood what do you mean by an AND gate, what is an OR gate and what's a NOT gate. So using these basic gates we are going to design this circuit. So here they have given to plot an AND gate because this is A multiplied by B. So we are going to put 2 inputs with an AND symbol. Similarly we also have an AND gate for A and C. So we have 2 inputs, that is A and C bar. It's because we have C bar, I'm going to use a complement for C input. I also have 3 inputs here, B bar, A bar and C. These are all AND gates. So I represent it as B bar, A bar and C, which are all ANDed. Now after ANDing all this, we have a plus symbol in between. It's nothing but an OR symbol. So how to represent this in a circuit? I take this as an input and I draw an OR symbol, a common for all these 3 inputs. So once if I put this as an input for this OR symbol, finally I get an expression which has been given in your question. So this is how we draw a circuit diagram for given any kind of an expression. Now let's see how to draw a circuit diagram for another example. We have given an example of f of x y z, which is equals to x plus y dot x bar plus z bar dot y plus z. Now again we have or here in between x and y. So I replace this symbol, that is symbol of an or, and I have x bar plus z bar. So x bar, z bar, and I or it. Similarly I will or y and z. So y and z I or it. Finally I have an AND operation in between this expression, that is AND. So I take all these inputs and I put it into one single channel, and that's an AND gate. So once you get this AND gate, finally after resolving these expressions you get the desired expression. Now one of the important technique which we use for designing circuits, that is nothing but a universal gates. What's a universal gate? Universal gate is a gate where all the basic gates can be designed using NAND and NOR gates. This concept is called as universal gates. Now why these universal gates are used to design circuits? It's because when we compare the basic gates and derived gates, when we compare these gates with universal gates, these are quite less expensive and very easy to design. The one more advantage of using universal gates is that we can design basic gates using NAND and NOR gates. That becomes very efficient to design circuits. That's why we go for universal gates. Now let's try understanding what do you mean by the implementation of basic gates using NAND gates. So in this example, we are going to study how to design the basic gates, that is AND gate, OR gate and NOT gate, by using only NAND gate. Now if you look at the symbol, I have X which is represented into two different wires, and I have a symbol of NAND gate here. So this is nothing but what? Input which I have given X, here it's divided into 2x. If you look at this expression, I have divided into x dot x whole bar. So when we apply a De Morgan's theorem for this, if you break up this x dot x whole bar, it becomes x bar plus x bar. So we know that x bar plus x bar is nothing but x bar. So that is where we get an output for this. When my input is x, my output would be x bar, and this is a NOT gate which we are trying to represent in the form of NAND gate. Similarly, we would also implement a AND gate as well as. Now let's see how to design the AND gate using NAND gate only. Now this is the symbol where I input x and y using NAND gate. Again I divide this x dot y whole bar into two different wires. So when I divide it, what do I get? It is xy whole bar dot x dot y whole bar, the raised to bar, because I'm taking a NAND gate for these two inputs. So if you further divide, it becomes by applying De Morgan's theorem, we get xy double bar plus xy double bar, which is nothing but xy plus xy. We also know that anything which is added with the same variable, it remains with the same variable as it is. That is xy plus xy will remain xy only. So we get an output as xy, which is nothing but a AND gate which is represented in the form of NAND gate. In the similar way, we would also like to design an OR gate using NAND gates only. Now if I have input as x and y, I divide this x into two parts, so I get x dot x whole bar. Similarly, I also give the input as y, where it becomes y dot y whole bar. So once if I use this as an input for the another NAND gate, because if you see that x dot x whole bar is nothing but x bar, similarly y dot y whole bar is nothing but y bar. So for this symbol, I'm giving input as x bar y bar, it becomes x bar dot y bar the whole bar. Now if I break this and apply De Morgan's theorem, I get it as x double bar plus y double bar, which is nothing but again x plus y. So this is how we design a basic gates using NAND gates only. Now let's try designing a circuit using NAND gates only. Now let's say a question is given to you where we are supposed to draw a circuit diagram for yz plus xz, that is in terms of NAND gates only. Now how do we represent this? Let's check it out. So your function yz plus xz can be represented as y NAND z, that is in between these two I'm representing NAND, as well as for plus I'm representing it as NAND, and in between xz I'm representing x NAND z. Now I'm using this NAND, it's because I'm supposed to draw this circuit using NAND gates only, and that's the reason no matter whether you have AND or OR in between, I'm replacing those operators with NAND. Now how do I draw the diagram for this? We know what is the symbol of NAND symbol and the inputs are Y and Z. So let's try drawing it. I give two inputs Y, Z and I'm using a NAND symbol for this. Similarly, I draw X, NAND, Z. Now for these two inputs, I have to NAND this again. So again I'll draw one more NAND gate where after giving the inputs for this, I get this as YZ whole bar and this I get it as XZ whole bar. So if I give the input for this, what will I get the final result? It is YZ whole bar and this XZ whole bar raised to whole bar. I can apply De Morgan's theorem. After dividing this, we get it as YZ plus XZ, which is the given function. Now let us take one more example to draw the circuit diagram using NAND gates only. The given expression is AB plus BC plus CD. Get with one more example. We have an equation with f of ABC where I'm trying to represent the circuit in the form of NAND gate. So we have two inputs here, that is A and B, but it is a NAND gate, so we are going to represent it with NAND symbol. Similarly for BC and CD. So no matter whatever expression is given, we are going to put a NAND in between A and B, and even if we have plus symbol, we are going to represent it with NAND. And this we are doing is just because we have to design this circuit in terms of NAND gate. So further, after giving an inputs for AB, BC and CD, we are going to get this as an inputs because I'm going to add this with NAND symbol. So once if I add this using these inputs, so what do I get is this would be input, that is AB bar, BC bar, CD bar, the whole bar, because it's a NAND gate. So if I apply De Morgan's theorem, that would be, if you break this, I get it as plus because it's multiplication. So after removing this double bar, we get it as AB plus BC plus CD, and that is nothing but the given equation. Similarly, we draw another example for the circuit diagram with function which is given as AB bar C plus C bar B, and this also we are going to design it using NAND gates only. So as I said, whatever may be the expression or the function, we are going to replace an AND in between these variables and for this operator as well. If you look at this expression, we have A NAND, it's complement of B. That's why I represent it in bracket as not B, because it's complement of B. And then we have NAND C. This entire thing is one operator, or you can call it as operand. Similarly, plus symbol I replace it and NAND. So this is altogether one operand. So I'll put it in a bracket saying that C bar is nothing but not C, and multiplied by B, and it is nothing but NAND B. So for this expression, we are going to design a circuit. We know the symbol of A NAND not B. So symbol for this would be with three inputs A, B and C. That is A not B. Not is again we are going to represent it in the form of NAND gates only. So this becomes my not, that is B complement of B, and this is input C. Then for this I'm going to draw a separate circuit, that's not C, that's complement of C using NAND gates, and this would be input of B. So when I give this as an input, I get this as output for this signals as A, B bar, C the whole bar, because it's a NAND gate. For this, when I give input as CB, it becomes C bar B the whole complement. So if I give these inputs for this circuit, that's for NAND gate again. So what do I get is AB bar C the bar multiplied by C bar B bar raised to, since we have bubble, it becomes whole bar. So again apply De Morgan's theorem for this. We further divide it by applying De Morgan's theorem. The multiplication becomes plus, and you remain with AB bar C plus C bar B. Now let's try understanding how to implement the basic gates using NOR gates. Now in previous slide we understood as how to design basic gates using NAND gates. Now here we are trying to implement the basic gates using NOR gate only. Now how to design this? Let's see NOT gate to design it with using NOR gate. Now this is an input of X. This is symbol of NOR gate. So when I give input X, I get it as X bar. So when I divide X into two wires, I get X plus X whole bar, which is equals to X bar dot X bar. We know that X bar dot X bar is nothing but X bar. So here the meaning of NOT gate is when I give input as 0, my output will be 1. But the difference here is I'm designing this NOT gate using NOR symbol, NOR gate symbol. Now similarly we also can design an OR gate using NOR symbol. We have inputs as A and B, which I get it as A plus B whole bar because it's a NOR gate. So when I divide this into 2, that is A plus B whole bar, if we apply a De Morgan's theorem, we get it as A bar dot B bar, A bar dot B bar. If I give these two inputs for this circuit, what do I get is A bar B bar plus A bar B bar the whole bar because it's a NOR gate. So again apply a De Morgan's theorem, we classify it, we solve it, we get it as AB dot AB bar raised to bar, that is AB bar double bar dot AB double bar. So again if we apply De Morgan's theorem for this, we get it as A double bar plus B double bar dot A double bar plus B double bar. Then after we further solve it, we get it as A plus B because A double bar plus B double bar gets cancelled, you remain with only A plus B dot A plus B. We know that any variable multiplied with the same variable remains as it is, that is A plus B dot A plus B remains A plus B. So what did we get the output as? It's A plus B. What is A plus B? It's a OR gate. My input was A and B, I got output as A plus B, which is OR gate. But if you look at the diagram, we represented an OR gate in terms of NOR gate. Now similarly we are going to design an AND gate using NOR gate. How to do that? Let's say A is my input, I divide A into two wires and that becomes A plus A the whole bar, which is nothing but A bar dot A bar, which remains A bar as it is. Similarly if I give input as B with two different wires, I get it as B plus B whole bar, which is nothing but B bar dot B bar, which is equals to again B bar. So if I give this as an input for the AND gate, because for that I have to give this to solve the inputs of A and B. So if I apply here as an input with A bar and B bar, what I get is A bar plus B bar the whole bar because this is NOR gate. So again if I simplify this, I get it as A double bar dot B double bar. So final result what we get it is A dot B. And this A dot B is nothing but what? An AND gate for inputs A and B. Now, what we have done in this circuit is we have concluded an AND gate using NOR gate. Now let's see one example as how to draw a circuit with NOR gates only. In previous slides we saw how to design a circuit using NAND gates, and this would be an example to design for given expression with using NOR gates. So we have given a question to design a circuit for A plus B multiplied by B plus C multiplied by C plus D with only NOR gates. So as we done in previous slide, we are going to do the same thing, but only thing here is we are going to replace a NOR symbol in between the variables. So if you look at this A and B, in between I have plus, so there I will replace NOR. Even if I have dot operator here in between A plus B and B plus C, here also I replace NOR gate. Similarly I do it for B plus C, I replace B nor C, C plus D, I replace C nor D. In between these two I have dot. For that sake also I'll replace it as NOR. Why is that I'm replacing NOR here? Because we are going to design this circuit based on this NOR gates only. Now let's give an input for this first bracket, that is A and B, which is NOR gate. Similarly for B and C as input, similarly for C and D as input. So when we give this as input, we get an output as A plus B whole bar because it's a NOR gate. Similarly, it's B plus C the whole bar for this BC input. Similarly, C plus D whole bar for the input C and D. Now we have done only with this 1, 2 and 3 brackets, but we also have a NOR in between these 3 brackets. So I have to give us an input to produce this entire expression. So what I do is I give A plus B whole bar, B plus C whole bar, C plus D whole bar as an input for this circuit. So what happens if I give the input for this? This is what I get here. So I get it as A plus B bar plus B plus C bar plus C plus D bar, the whole bar here. It's because complement of we are using NOR gates. And as usual, again we apply De Morgan's theorem. We get it as A plus B double bar, because we have plus here, it becomes, we are breaking this symbol, plus becomes into, so we get it into brackets, B plus C double bar into C plus D double bar. So if we remove these double bars, we remain with the expression that is A plus B multiplied by B plus C multiplied by C plus D. And this we got it for what the equation they had given to design a circuit for NOR gates. So this is how we design a circuits using NAND and NOR gates only. So that's all for this video, students. Let's meet in next video. Thank you.